What is a virtual machine? A virtual machine is a compute resource that uses software instead of a physical computer to run programs and deploy apps. One or more virtual guest machines run on a physical host machine. So each virtual machine runs its own operating system and functions separately from the other virtual machines, even when they are all running on the same host. This means that, for example, a virtual Mac operating system virtual machine can run on a physical Windows PC. Virtual machine technology is used for many use cases across on-premises and cloud environments. More recently, public cloud services are using virtual machines to provide virtual application resources to multiple users at once for even more cost-efficient and flexible compute. Virtual machine implementations involve several components. At the base is the host, the underlying hardware system that runs the virtual machines. The Virtual Machine Manager, VMM, also known as a hypervisor, creates and runs virtual machines by providing an interface that is identical to the host, except in the case of para-virtualization. In this figure, we can see each guest process is provided with a virtual copy of the host. Usually, the guest process is in fact an operating system. A single physical machine can thus run multiple operating systems concurrently, each in its own virtual machine. There are several types of hypervisor. Let's talk about Hype2 first. Hype2 hypervisor are computer emulation applications that run on general-purpose operating systems. A Type 2 hypervisor allows users to run multiple operating systems simultaneously on a single platform. For example, a Windows 7 user can install a hypervisor application like a VMware workstation to run a Windows XP guest operating system on top of their Windows 7 host operating system. As an application, the Type 2 hypervisor is subject to performance, security, and reliability penalties. The hosted hypervisor incurs performance hits because it competes with other user applications like web browsers and email clients for system resources. Type 2 hypervisors are weak in reliability and security because they inherit vulnerability of the user-controlled host operating system. Type 1 hypervisors are computer emulation software tightly integrated with embedded operating systems that run transparent to the end user. Type 1 hypervisors gain a significant performance improvement over Type 2 hypervisors because they are self-hosted with embedded operating systems that are optimized for virtualization. Type 1 hypervisors significantly reduce the attack surface over Type 2 hypervisors by limiting access to the hypervisors to only system administrators, preventing end users and user applications from tampering with the hypervisor. Additionally, Type 1 hypervisor vendors control all the software that comprise the hypervisor package, including the virtual machine functions and the operating system functions, like device drivers and the I/O input-output stacks. Control over the software package prevents malicious software from being introduced into the hypervisor foundation. The limited access and the strong control over the embedded operating system greatly increase the reliability of Type 1 hypervisors. Type 0 is based on architecture that allows for higher levels of performance, reliability, and security over Type 1 hypervisors. Type 0 hypervisors is built with the minimum software components required to fully virtualize guest operating system and control information flow between guest operating systems. The Type 0 architecture removes the need for an embedded host operating system to support virtualization, allowing the hypervisor to run in an unhosted environment. This drastically differs from Type 1 monolithic architectures where the hypervisor is integrated into a host operating system, or Type 1 microkernel architectures where the hypervisor is controlled and assisted by a root or parent operating system. Other options include paravirtualization. Paravirtualization is an enhancement of a virtualization technology in which a guest operating system is modified prior to installation inside a virtual machine in order to allow all guest operating systems within the system to share resources and successfully collaborate rather than attempt to emulate an entire hardware environment. Oracle Java and Microsoft.NET use programming environment virtualization, in which VMM don't virtualize real hardware, but instead create an optimized virtual system. We have emulators. Emulators allow applications written for one hardware environment to run on a very different hardware environment. For example, emulators make it possible to run Windows on a Mac computer and vice versa. Application containment, which is not virtualization, but rather provides virtualization-like features by segregating applications from the operating system. Application containment is used to block harmful file and memory actions to other apps and the endpoint. Virtual machine first appeared commercially on IBM mainframes in 1972. For many years after IBM introduced this technology, virtualization remained in its domain. Now, the virtualization requirements called for fidelity. A VM provides an environment for programs that is essentially identical to the original machine. Performance. Programs running within that environment show only minor performance decreases. Safety. The virtual machine is in complete control of system resources. By the late 1990s, Intel CPU had become common, fast, and rich in features. And we know XEN, Zen, and VMware, though the two popular virtual machine created technologies still used today. Since that time, virtualization has expanded to include all common CPUs, many commercial and open source tools, and many operating systems. For example, the open source VirtualBox project provides a program that runs on Intel x86 and AMD 64 CPUs, and on Windows, Linux, Macs, and Solaris hosting operating systems. There are many benefits of using a virtual machine. For example, lower hardware cost. Many organizations don't fully utilize their hardware resources. Instead of investing in another server, organizations can spin up virtual servers instead. Quicker desktop provision and deployment. Deploying a new physical server often takes numerous time-consuming steps. However, with visualized system, organizations can deploy new virtual servers quickly using secure, pre-configured server templates. Smaller footprint, utilizing visualization reduced the office space need to maintain and extend IT capabilities while also freeing up desk space to support more employees. Visualization streamlines disaster recovery by replicating your servers in the cloud. Since virtual machines are independent of the underlying hardware, organizations don't need the same physical servers offsite to facilitate a secondary recovery site. In the event of a disaster, employees can be back online quickly with a cost-effective backup and a disaster recovery solution. Portability. It's possible to seamlessly move virtual machines across virtual environments and even from one physical server to another, with minimal input on the part of IT teams. Virtual machines are isolated from one another and have their own virtual hardware, making them hardware independent. Moving physical servers to another location is a more resource-intensive task. Many IT departments spend at least half of their time managing routine administrative tasks. However, with virtualization, it's possible to partition one physical server into several virtual machines. Administrators can deploy and manage multiple operating systems at once from a single physical server. One of the tools that make it possible is templating, in which one standard virtual machine image, including an installed and configured guest operating system and applications, is saved and used as a source for multiple running virtual machines. Some virtual machines include a live migration feature that moves a running guest from one physical server to another without interrupting its operation or active network connections. Cloud computing is the delivery of on-demand computing services, from applications to storage and processing power, typically over the internet and on a pay-as-you-go basis. When organizations store data in virtual data centers or access programs using an internet connection, instead of relying on their device's hard drive or on-premises IT infrastructure, it means they are operating in the cloud. Although the virtual machine concept is useful, it is difficult to implement. Much work is required to provide an exact duplicate of the underlying machine. This is especially a challenge on dual-mode systems, where the underlying machine has only user mode and a kernel mode. An important concept to implement virtual machine is the implementation of a virtual CPU, vCPU. vCPU doesn't execute code, rather it represents the state of the CPU as the guest machine believed it to be. For each guest, the virtual machines maintain a vCPU representing that guest's current CPU state. When the guest is context switched on a CPU by the virtual machine, information from the vCPU is used to load the right context, much as a general-purpose operating system would use, the PCB. On a typical dual-mode system, the virtual machine guest can execute only in user mode. The kernel, of course, runs in kernel mode, and it is not safe to allow user-level code to run in kernel mode. Just as the physical machine has two modes, so must the virtual machine. Consequently, we must have a virtual user mode and a virtual kernel mode, both of which run in a physical user mode. Those actions that cause a transfer from user mode to kernel mode on a real machine must also cause a transfer from virtual user mode to virtual kernel mode in the virtual machine. Each operating system was designed to be in total control of the system, which makes it impossible for two or more operating systems to be executing concurrently on the same platform, unless total control is taken away from them by a new layer of control software, the Virtual Machine Manager. The Virtual Machine Manager will have to be able to intervene when one operating system is attempting to do something that conflicts with what another operating system wants to do. With the new virtualization technology instructions, the CPU is able to trap such attempts and allows the Virtual Machine Manager to emulate the effect that is desired by one operating system, but in a manner that doesn't intervene with another operating system. Attempting a privileged instruction when in user mode causes an error to occur, thus leading to trap state. And after this, the Virtual Machine Manager gets control and analyzes the error, executes the operation as attempted by the guest, and then return the control back to guest in user mode. Note, kernel mode privileged command runs slower due to trap and emulate. We can see privileged instruction runs slower. All non-privileged instructions run natively on the hardware, providing the same performance for guests as native applications. Privileged instructions create extra overhead, however, causing the guest to run more slowly than it would natively. In addition, the CPU is being multi-programmed among many virtual machines, which can further slow down the virtual machines in an unpredictable way. Some CPU don't have a clean separation of privileged and non-privileged instructions. Backward compatibilities throughout the lifetime prevents change that would have made virtualization easier through many generations. For example, the command popf loads the flag register from the contents of the stack. If the CPU is in privileged mode, all of the flags are replaced from the stack. If the CPU is in user mode, then only some flags are replaced and the others are ignored. Because no trap is generated if popf is executed in user mode, the trap and the emulate procedure is rendered uselessly. The binary translation technique can be used to solve those special instructions. The basic steps are as follows. If the guest vCPU is in user mode, the guest can run its instructions natively on a physical CPU. If the guest vCPU is in kernel mode, then the guest believes that it is running in kernel mode. The virtual machine manager examines every instruction the guest executes in virtual kernel mode by reading the next few instructions that the guest is going to execute, based on the guest program counter. Instructions other than special instructions are run natively. Special instructions are translated into a new set of instructions that perform the equivalent task, for example, changing the flags in the vCPU. The binary translation is implemented by translation code within the virtual machine manager. The code reads native binary instructions dynamically from the guest on demand and generates native binary code that executes in place of the original code. The replacement code for each instruction that needs to be translated is cached. All later executions of that instruction run from the translation cache and needn't be translated again. If the cache is large enough, this method can greatly improve performance. A common method used in both trap and emulate in the binary translation is to use nested page tables, NPTs. Each guest operating system maintains one or more page tables to translate from virtual to physical memory. The virtual machine manager maintains NPTs to represent the guest page table state, just as it creates a vCPU to represent the guest CPU state. The virtual machine manager knows when the guest tries to change its page table, and it makes the equivalent change in the NPT. When the guest is on the TPU, the virtual machine manager puts the pointer to the appropriate NPT into the appropriate CPU register to make that table the active page table. If the guest needs to modify the page table, for example, for filling a page fault, then the operation must be intercepted by the virtual machine manager and appropriate changes made to the nested and system page tables. Unfortunately, the use of NPTs can cause TLB misses to increase, and many other complexities need to be addressed to achieve reasonable performance. The more hardware support available within the system, the more feature-rich and stable the virtual machines can be, and the better way they can perform. In the Intel ch18 CPU family, Intel added new virtualization support, the VTX instructions, in successive generations beginning in 2005. Now, binary translation is no longer needed. AMD virtualization technology in 2006 defines two new modes of operation, host and guest, thus moving from dual mode to a multi-mode processor. In guest mode, the virtualized operating system thinks it is running on a native hardware and sees whatever devices are included in the host definition of the guest. If the guest tries to access a virtualized resource, then control is passed to the virtual machine manager to manage that interaction. AMD and Intel have also addressed memory management in the virtual machine. The nested page tables were implemented in hardware to allow the virtual machine manager to fully control paging while the CPU accelerates the translation from virtual to physical addresses. DMA, direct memory access, and interrupts can also be hardware assisted. The NPTs add a new layer when representing the guest view of logical to physical address translation. This figure shows the extra translation work performed by the hardware to translate from a guest virtual address to a final physical address. A TLB miss results in a performance penalty because more tables, the guest and the host page tables, must be traversed to complete the lookup. Let's begin with the virtual machine life cycle. Virtual machine is created. Its creator gives the VMM certain parameters. These parameters usually include the number of CPUs, amount of memory, networking details, and the storage detail that the VMM will take into account when creating the guest. The VMM then creates the virtual machine with those parameters. In the case of a Type 0 hypervisor, the resources are usually dedicated. In this situation, if there are not two virtual CPUs available and unallocated, the creation request in our example will fail. For other hypervisor types, the resources are dedicated or virtualized, depending on the type. When the virtual machine is no longer needed, it can be deleted. The VMM frees up any unused disk space and then removes a configuration associated with the virtual machine. We can see virtual machine is very easy to be created. It calls VM sprawl, also known as a virtualization sprawl, happens when an administrator can no longer effectively control and manage all the virtual machines on a network. This can happen with rapidly growing networks when multiple virtual machines are set up for use by different departments. Type 0 hypervisors have existed for many years under many names, including partitions and domains. They have a hardware feature, and that brings its own positive and negatives. Operating systems need do nothing special to take advantage of their features. The VMM itself is encoded in the firmware and loaded at the boot time. In turn, it loads the guest images to run each partition. Type 0 virtualization is very close to raw hardware execution. I/O has some difficulty because it is not easy to dedicate I/O devices to guests if there are not enough. Each guest operating system in a Type 0 hypervisor is a native operating system with a subset of hardware made available to it. Because of that, each can have its own guest operating systems. Other types of hypervisors usually cannot provide this virtualization within virtualization functionality. Type 1 hypervisor, also called a bare metal hypervisor, is a layer of software we install directly on top of a physical server and its underlying hardware. There is no software or any operating system in between, hence the name bare metal hypervisor. A Type 1 hypervisor is proven in providing excellent performance and stability since it doesn't run inside Windows or any other operating system. By using Type 1 hypervisors, data center managers can consolidate more operating systems and applications onto fewer systems. Using snapshots and cloning, the system can save the state of guests and duplicate those guests, a much easier task than restoring from backups or installing manually or via scripts and tools. Type 1 hypervisor run on standard hardware. They can run on Type 0 hypervisors, but not on other Type 1 hypervisors. Guests generally don't know they are running on anything but the native hardware. Type 1 hypervisor run in kernel mode, and they implement device drivers for the hardware they run on, since no other component could do so. Because they are operating systems, they must also provide CPU scheduling, memory management, I/O management, protection, and even security. Another type of Type 1 hypervisor includes various general-purpose operating systems with VMM functionality. Here, an operating system such as a Red Hat Linux, Windows, or Oracle Solaris performs its normal duties as well as providing a VMM allowing other operating systems to run as a guest. Because of their extra duties, these hypervisors typically provide fewer virtualization features than other Type 1 hypervisor. In many ways, they treat a guest operating system as just another process, but they provide special handling when the guest tries to execute special instructions. Type 2 hypervisor runs inside of an operating system of a physical host machine. So this is why we call Type 2 hypervisors hosted hypervisors, as opposed to Type 1 hypervisors that run directly on the hardware. Hosted hypervisors have one software layer underneath. So in this case, we have a physical machine, which is the hardware. Then on that is an operating system installed on the hardware, such as Windows, Linux, Macs. And a Type 2 hypervisor software is within that operating system. Then we have the actual instance of guest virtual machines. Type 2 hypervisors are typically found in environments with a small number of servers. What makes them convenient is that you don't need a management console to another machine to set up and manage your virtual machines. You can do all of this on the server where you install the hypervisor. They are not any different from other applications you have in your operating system. When you launch a virtual machine, you get another window to perform all tasks. The VirtualBox by Oracle is an example of a Type 2 hypervisor interface. Type 2 hypervisors tend to have poor overall performance than Type 0 or Type 1. For example, a user needs administrative privileges to access hardware features. If the virtual machine manager is being run by a standard user without additional privileges, the VMM cannot take advantage of these features. On the other hand, a Type 2 hypervisors run on general-purpose operating systems. So for example, a student can use a Type 2 hypervisor to test a non-native operating system without replacing the native operating system. In computing, parallel virtualization is a virtualization technique that presents a software interface to the virtual machines which is similar, yet not identical to the underlying hardware-software interface. The intent of the modified interface is to reduce the portion of the guest execution time spent performing operations which are substantially more difficult to run in a virtual environment compared to a non-virtualized environment. The parallel virtualization provides specifically the defined hooks to allow the guest and the host to request and acknowledge these tasks, which would otherwise be executed in the virtual domain, where execution performance is worse. A successful parallel-virtualized platform may allow the virtual machine monitor, VMM, to be simpler by relocating execution of critical tasks from the virtual domain to the host domain, or reduce the overall performance degradation of machine execution inside the virtual guest. The open source Zen project is an example of a parallel virtualization that virtualized the processor and the memory using a modified Linux kernel and virtualized the I/O using custom guest operating system device drivers. Each device has a circular buffer shared by guest and the VMM by shared memory. In this figure, we can see Zen allow efficient I/O as well as a good I/O-related communication between the guest and the VMM. Read and write data are placed in this buffer. For memory management, Zen didn't implement nested page tables. Rather, each guest had its own set of page tables, set to read only. Zen required the guest to use a specific mechanism, a hypercall from the guest to the hypervisor VMM, when a page table change was needed. This meant that the guest operating system's kernel code must have been changed from the default code to these Zen-specific methods. To optimize performance, Zen allowed the guest to queue up multiple page table changes asynchronously by hypercalls and then check to ensure that the changes were complete before continued operation. Zen allowed virtualization of x86 CPUs without the use of binary translations. Nowadays, Zen has taken advantage of hardware features supporting virtualization. As a result, it no longer requires modified guests and essentially doesn't need the parallel virtualization method. Parallel virtualization is still used in other solutions, however, such as Type 0 hypervisors. We know Oracle Java has many features that depend on its running in the Java Virtual Machine, JVM, including specific methods for security and memory management. We can define a virtual environment based on APIs that provides a set of features that we want to have available for a particular language and programs written in that language. Java programs run within the JVM environment, and the JVM is compiled to be a native program on system on which it runs. So this arrangement means that Java programs are written once and then can run on any system, including all of the major operating systems on which a JVM is available. It's as similar as an interpreted language, which run inside programs that read each instruction and interpret it into native operations. Emulation is useful when the host system has one system architecture and the guest system was compiled for a different architecture. For example, suppose a company has replaced its outdated computer system with a new system, but would like to continue to run certain important programs that were compiled for the old system. The programs could be run in an emulator that translates each of the outdated system's instructions into the native instruction set of the new system. Emulation can increase the life of programs. Also, the main challenge of emulation is performance. The emulation instruction run much slower than native instructions because it may take 10 instructions on the new system to read, pass, and simulate an instruction from the old system. The slow performance can be balanced by the usefulness of being able to run old programs on newer, incompatible hardware or run games designed for old consoles on modern hardware. A container is a virtual runtime environment that runs on top of a single operating system kernel, and it emulates an operating system rather than the underlying hardware. A container engine is managed environment for deploying containerized applications. Starting with version 10, Oracle Solaris has included containers or zones that create a virtual layer between the operating system and the applications. So in this system, only one kernel is installed, and the hardware is not virtualized. Rather, the operating system and its devices are virtualized, providing processes within a zone with the impression that they are the only processes on the system. One or more containers can be created, and each can have its own applications, network stacks, network address and ports, user accounts, and so on. CPU and memory resources can be divided among the zones and a system-wide process. Each zone, in fact, can run its own scheduler to optimize the performance of its applications on the allotted resources. So this figure shows Solaris 10 system with 2 containers and a standard global user space. Let's take a look of operating system in virtualization. So how do virtual machine manager schedule CPU use when guest operating systems believe they have dedicated CPU? How can memory management work when many guests require large amounts of memory? In virtualization, even a single CPU system frequently acts like a multiprocessor system. The VMM, Virtual Machine Manager, has a number of physical CPU available and a number of threads to run on those CPUs. The threads can be VMM threads or guest threads. Guests are configured with a certain number of virtual CPUs at creation time, and that number can be adjusted throughout the life of the virtual machine. When there are enough CPU to allocate the requested number to each guest, the VMM can treat the CPUs as dedicated and schedule only a given guest thread on that guest CPUs. So in this situation, the guests act much like native operating system running on native CPUs. When there are not enough CPUs available, in this case we call it overcommitment, in which the guests are configured for more CPUs than exist in the system. So a VMM here can use standard scheduling algorithms to make progress on each thread, but can also add a fairness aspect to those algorithms. Consider a time-sharing operating system that tries to allot 100 milliseconds to each time slice to give users a reasonable response time. Within a virtual machine, this operating system receives only what CPU resources the virtualization system gives it. So 100 millisecond time slice may take much more than 100 milliseconds of virtual CPU time. Depending on how busy the system is, the time slice may take a second or even more, resulting in very poor response time for users logged into that virtual machine. The effect on a real-time operating system can even be more serious. Commonly, the time of day clocks in virtual machines are incorrect because timers take longer to trigger than they would on dedicated CPUs. To correct this, the VMM makes an application available for each type of operating system that the system administrators can install into the guest. This application corrects clock drift and can have other functions such as virtual device management. In virtualized environment, there are more users of memory, the guest and their applications as well as the VMM, leading to more pressure on memory use. For example, VMware first calculates how much real memory each guest should use. Then it also estimates targeted configured memory for the guests and other factors such as overcommitment and the system load. VMware used 3 low-level mechanisms to reclaim memory from the guests. The first approach is to provide double paging. VMM has its own paging replacement algorithms and load page into a backing store that the guests believe is physical memory. This is not a preferred approach. VMM use it when other options are not available. A common solution for the VMM to install each guest a pseudo device drivers or kernel module that the VMM controls. Pseudo device drivers are parts of the kernel that act like device drivers but don't correspond to any actual hardware in the machine. A pseudo device driver was used to implement a memory balloon that could vary the memory pressure on the guest operating system. Memory ballooning is a memory management feature used in most virtualization platforms, which allows a host system to artificially enlarge its pool of memory by taking advantage or reclaiming unused memory previously allocated to various virtual machines. The third common method for reducing memory pressure is for the VMM to determine if the same page has been loaded more than once. If this is the case, the VMM reduces the number of copies of the page to 1 and maps the other users of the page to that one copy. Usually, device drivers can be dynamically loaded and unloaded. Virtualization takes advantage of this built-in flexibility by providing specific virtualized devices to guest operating systems. But overall, I/O is complicated for VMMs. The less the hypervisor has to do to enable I/O for its guest, the faster the I/O can occur. With Type 0 hypervisors that provide direct device access, guests can often run at the same speed as the native operating systems. With direct device access in Type 1 and Type 2 hypervisors, performance can be similar to that of native operating system if certain hardware support is present. The hardware needs to provide DMA pass-through with facilities like a VTD, as well as direct interrupt delivery. In networking, with bridged networking, the virtual network adapter in the virtual machine connects to a physical network adapter in the host system. The host network adapter enables the virtual machine to connect to the LAN that the host system uses. Bridged networking works with both wired and wireless host network adapter. Alternatively, the VMM can provide a network address translation, NAT address. The NAT address is local to the server on which the guest is running, and the VMM provides routing between the broader network and the guest. An important question in determining how virtualization works is this. If multiple operating systems have been installed, what and where is the boot disk? The solution to this problem depends on the type of hypervisor. Type 0 hypervisors often allow root disk partitioning, partly because these systems tend to run fewer guests than other systems. Type 1 hypervisors store the guest root disk and the configuration information in one or more files in the file system provided by the VMM. Type 2 hypervisors store the same information in the host operating system's file systems. In essence, a disk image containing all of the content of the root disk of the guest is contained in one file in the VMM. The associated disk image of the guest can be duplicated, copied, and moved to other systems. Frequently, VMMs provide a mechanism to capture a physical system as it is currently configured and convert it to a guest that the VMM can manage and run. So this physical to virtual conversion reads the disk blocks of the physical system disk and stores them in files on the VMM system or on shared storage that VMM can access. VMM also provides a virtual to physical procedure for converting a guest to a physical system. Live virtual machine migration is the process of moving a running virtual machine from one physical host to another with minimal disruption to ongoing services. It is a powerful tool that facilitates hardware maintenance, load balancing, fault tolerance, and power savings in clusters in the data center. The VMM migrates a guest by the following steps. 1. The source VMM establishes a connection with the target VMM and confirms that it is allowed to send a guest. 2. The target creates a new guest by creating a new vCPU, new nested page table, and other state storage. 3. The source sends all read-only memory pages to the target. 4. The source sends all read-write pages to the target, marking them as clean. 5. The source repeats step 4, because during the step, some pages will probably modified by the guest and are now dirty. So these pages need to be sent again and marked again as clean. 6. When the circle of step 4 and 5 becomes very short, the source VMM freezes the guest, sends the vCPU's final stage, other state details, and the final dirty pages, and tells the target to start running the guest. Once the target acknowledges the guest is running, the source terminates the guest. VM Workstation enables users to create and run virtual machines directly on a single Windows or Linux desktop or laptop. Those virtual machines run simultaneously with the physical machine. Each virtual machine runs its own operating system, such as Windows or Linux. So VMware Workstation is a prime example of a Type 2 hypervisors. This figure shows the example of architecture of VMware Workstation. In this situation, Linux is running as the host operating system, and FreeBSD, Windows NT, and Windows XP are running as guest operating systems. At the heart of VMware is the virtualization layer, which abstracts the physical hardware into isolated virtual machines running as guest operating systems. Each virtual machine has its own virtual CPU, memory, disk drives, network interfaces, and so on. The physical disk that the guest owns and manages is really just a file within the file system of the hosting operating system. To create an identical guest or move a guest, we can simply just duplicate this file copy and move it to other system. A Java Virtual Machine, JVM, is a virtual machine that enables a computer to run Java programs as well as programs written in other languages that are also compiled to Java bytecode. The Java Virtual Machine is an abstract or virtual computer defined by a specification. It is a part of Java runtime environment. The garbage collection algorithm used and any internal optimization of the Java Virtual Machine instructions, so their translation into machine code, are not specified. The main reason for this omission is to not unnecessarily constrain implements. Any Java application can be run only inside some concrete implementation of the abstract specification of the Java Virtual Machine. Java objects are specified with the class construct. A Java program consists of one or more classes. For each Java class, the compiler produces in architecture new to bytecode output .class file that will run on any implementation of the JVM. The JVM may be implemented in software on top of a host operating system, such as Windows, Linux, and Macs, or part of a web browser. Alternatively, the JVM may be implemented in hardware on chip, specifically designed to run Java programs. If the JVM is implemented in software, the Java interpreter interprets the bytecode operations one at a time. A faster software technique is to use ch18 just-in-time compiler. A just-in-time ch18 compiler is a feature of the runtime interpreter that instead of interpreting bytecode every time a method is invoked, will compile the bytecode into the machine code instructions of the running machine, and then cache it and invoke the object code instead. Current research is extending the use of virtualization. Unix kernels aim to increase efficiency and decrease security attack service by compiling an application, its libraries, and the kernel resources the application needs into one binary with one address space that runs within a virtual machine. Within the class of partitioning hypervisors are the Quest, V, EVM, Extratom, Siemens Jailhouse project. These are separation hypervisors that use virtualization to partition separate system components into a chip-level distributed system. Secure shared memory channels are then implemented using hardware-extended page tables so that separate sandboxed guests can communicate with each other. Those applications can be used in the areas of robotics, self-driving cars, and the Internet of Things.